11.4 Tangent lines and derivatives. Our goal for this section is to discuss tangent lines, slopes of tangent lines, and how it relates to the derivative. So differential calculus is the study of the derivative. The process of computing the derivative is called differentiation. So what is a derivative? We can define a derivative three different ways. 1, it's a rate of change. 2, it's the slope of a tangent line. And 3, it's the limit of a difference quotient. We're going to look at 1, the rate of change, later on. In this section, I'm going to focus on 2 and 3, the slope of a tangent line and the limit of a difference quotient. Together, those two are going to give us our formal definition for a derivative. So let's consider the slope of a secant line and the slope of a tangent line and how they relate. So a secant line looks like this. There's the picture. It's a line that goes through 2 points on a graph. Now I'm interested in looking at the slope of it. The slope of a secant line is the slope of the line through 2 distinct points on the graph of the function. Now the tangent line, on the other hand, this is what it looks like. And I want to know what's the slope of a tangent line. And the slope of a tangent line is the slope of the curve at the point of tangency on the graph of the function. Alright, so here we have a curve. It's like a parabola shape. And we have a secant line, the line in blue. And we have a tangent line, the line in red, that's a tangent at point P. Alright, so we want to observe what happens as point Q approaches point P. So imagine Q sliding down the curve of that function towards point P. See what happens to secant lines? So as Q gets closer and closer to P, the secant line gets closer and closer to that of the tangent line. Okay, so I want to rewrite points P and Q as ordered pairs. I'm going to imagine the distance between P and Q as h. That's the distance between those two. So the x value for P, that ordered pair, is just x, and the x value for the ordered pair Q, that point, would be x plus h. And that's going to give me my f of x values, my y values. I'm going to write those in. And instead of calling point P P, I'm going to call it x comma f of x. And point Q becomes x plus h comma f of x plus h. This is going to help me get the slope of the secant line. Alright, so the secant line. The secant line through 2 distinct points, x comma f of x, that was point P, and x plus h comma f of x plus h, that was point Q, on the graph of a function, f of x, has the slope. Basically, it's the change in y over the change in x, or you might remember that as rise over run from an algebra class. So plugging in what your y's would be, the difference of y values in the numerator, and then the difference of x values in the denominator, and then cleaning up, you get f of x plus h minus f of x over h. So that's the slope of the secant line. This expression is called the difference quotient. Okay, so let's look at the tangent line. The slope of the tangent line at a point on the graph of a function is given by f prime of x equals the limit as h approaches 0, and this expression here is the slope of the secant line. H was the distance between point P and point Q, and we were sliding Q towards point P in the previous animation. So the distance is getting smaller and smaller, so h, that distance, is approaching 0. So this is the limit of slopes of secant lines. Basically, this is what it looks like in math terms, what we saw visually as those blue secant lines were approaching the red tangent line. So f was the little apostrophe, and the x in parentheses is read f prime of x. So now we have a definition for the derivative. The derivative of f is given by f prime of x, that's how it's denoted, equals the limit as h approaches 0 of that difference quotient, provided the limit exists. When the limit exists, we say that f is differentiable. Note that f prime is also a function of x, and we'll see that more clearly when we do some derivatives. Derivative notation. These are all different ways that we can denote a derivative. Mostly I'll be using the first three that are listed there, f prime of x, y prime, and dy over dx. Notes on the derivative as a function. You can think of the derivative as a function that gives the slope of the function f of x at any point on the graph of f of x, provided the graph has a tangent line at that point. I'll bring this up again later. The domain of f prime of x consists of all values of x in the domain of f of x for which the limit exists. And we say that f of x is differentiable on the interval a to b if f prime of x exists for all x on that interval. In this limit, x is treated as a constant because it does not change as h approaches 0. So to calculate f prime of x using the limit definition, there's basically 4 steps. The first step is to find f of x plus h. The second step is to find and simplify f of x plus h minus f of x. Step 3 is to divide by h and simplify. So you're looking for that difference quotient. And step 4, finally to compute the derivative, you have to take the limit as h approaches 0 of that difference quotient. So you have 4 steps to finding the derivative using the limit definition. Example 1, compute f prime of x using the limit definition. So we want to find the derivative of that function. So the first step is to find f of x plus h. So you plug in x plus h everywhere there was an x. Now the first term, x plus h squared, you can expand that, and the second term you can distribute the negative 3 through. This is what you get. Step 2, you want to find f of x plus h minus f of x. So we're taking our answer from step 1 and we're subtracting the original function. So this is what we're looking for. We're going to distribute that negative through. This is what we get. And then combining like terms and canceling terms. This is how it simplifies. And then step 3, we want to divide the answer we got from step 2 by h. So this is what we want to find now. And we want to simplify this. Notice how there's an h in each term in the numerator. We can factor out an h in the numerator. Then the h in the numerator and the denominator cancel, and this is what I get. The last step is to finally take the limit of that difference quotient, which is what I found in step 3. So I'm taking the limit as h approaches 0 of 2x plus h minus 3. And I get 2x minus 3. I use direct substitution. I plug 0 in for h. So the derivative f prime of x equals 2x minus 3. That's my answer. Example 2. Find the derivative of f of x equals x squared plus 1 using the limit definition. Use the derivative to find the slope of the function f of x at x equals 0 and at x equals 1. So let's find the derivative first. So step 1, we need to find f of x plus h. So I plug x plus h in where I see an x. I can expand that. This is what I get. Step 2, I have to subtract f of x from the answer I got in step 1. So this is what I'm trying to find. I distribute that negative through. This is what I get. And then canceling and combining terms, it simplifies to 2xh plus h squared. Step 3. Now I'm going to divide the answer I got from step 2 by h. Notice how there's an h in each term in the numerator. I can factor out an h, and then I can cancel the h in the numerator and the denominator. So I get 2x plus h. Lastly, I take the limit as h approaches 0 of the difference quotient, which is what I got in step 3. So I'm taking the limit as h approaches 0 of 2x plus h. Using direct substitution and plugging 0 in for h, I get 2x. So the derivative, f prime of x, is equal to 2x. So the derivative is f prime of x equals 2x. So the derivative is a function itself that's going to tell me what the slope is of the original curve at any point on that curve, provided the limit existed. So the rest of this question is to use the derivative, there's the derivative, to find the slope of the function at x equals 0 and at x equals 1. So to find the slope at x equals 0, I just plug 0 into the derivative. So my slope is 0 at that point. To find the slope at x equals 1, I plug 1 into the derivative and I get 2. So the slope is 2 at that point. Definition of a tangent line. Now so far we've been finding the slope of a tangent line, but now we want to find the actual equation of a tangent line. So assume that f of x is differentiable at x equals a. The tangent line to the graph of y equals f of x at point a comma f of a is the line through that point with slope f prime of a. The equation of the tangent line in point slope form is given by the following. Y minus f of a equals f prime of a times x minus a. Now from algebra, this is how you probably remember it. Y minus y1 equals m times x minus x1, where m is the slope and x1, y1 is the point of tangency. Note that slope-intercept form is y equals mx plus b, where m is the slope and b is the y-intercept. A lot of times after you find your equation of a tangent line, you will be asked to put it in slope-intercept form. Example 3. Using the previous example, find equations of the tangent lines at x equals 0 and x equals 1. Write in slope-intercept form, and then sketch the graph of the function and the tangent lines. Okay, so from the previous example, this is the information we had gotten. We had the original function, f of x equals x squared plus 1. The derivative, f prime of x equals 2x. The slope at x equals 0 was 0, and the slope at x equals 1 was 2. So the first equation, we have the point 0, 1 and slope m equals 0. Now how do we get this point 0, 1? You plug 0, the x value, into the original equation to get the corresponding y value. Then we use point slope form. We plug in 1 for y1, 0 for m, and 0 for x1. And then we simplify. So I get y equals 1. So that's the equation of the first tangent line. For the second tangent line, we have the point 1, 2 and slope m equals 2. How did I get that point? You plug the x value 1 into the original equation to get the corresponding y value, 2. Then, using point slope form, plug in our y1 value, our m value, and our x1 value. So 2, 2, and 1. So after you plug in your known numbers, then you simplify, distribute that 2 through on the right-hand side, and then set y equal to everything else, solve for y, and you get y equals 2x. So that's the equation of the second tangent line. This is what it would look like if you graphed the original equation, f of x equals x squared plus 1, the blue line, the first tangent line, y equals 1, and the second tangent line, y equals 2x. So the first tangent line, the pink line, is tangent to the graph at 0, 1, that point. The second tangent line, y equals 2x, is tangent to the original equation, the graph of the original equation, at 1, 2, that point. Example 4. Use the function f of x equals negative x squared plus 2x minus 3. So for a, we want to compute f prime of x using the limit definition. Step 1, you find f of x plus h. So you plug in x plus h everywhere you see an x, and then cleaning that up, I've expanded x plus h squared. I'll have to distribute the negative through next, and I've distributed 2 through. So I have a negative here I have to worry about. This part has been expanded, and I've distributed a 2 through. Now if I distribute the negative through, this is what I get. And then step 2, I need to subtract the original equation from the answer in step 1. So this is what I have. I have a negative here that I need to distribute through. So this is what I get. And then combining terms, it simplifies to just 3 terms. So that's nice. Now step 3, I have to divide my answer from step 2 by h. So this is what I want to clean up. I can factor in h out of the numerator, Cancel the h's, and now I've got negative 2x minus h plus 2. Last step is to take the limit as h approaches 0 of the answer I got in step 3. So using direct substitution, I can just plug 0 in for h, and then I get negative 2x plus 2. So the derivative f prime of x is equal to negative 2x plus 2. Part B, find the slope at x equals 2. So I take my derivative, and I plug 2 into the derivative, and I get negative 2. So that's what the slope is when x equals 2. C, find an equation of the tangent line at x equals 2. Write it in slope-intercept form. So we have the point 2 comma negative 3 and slope m equals negative 2. Now how do we get that point? You have to plug 2 into the original equation to get the corresponding y value. So that's how we got 2 comma negative 3. Then we use point-slope form to find the equation of the tangent line. So I plug in negative 3 for y1, negative 2 for m, and positive 2 for x1. Cleaning this up, negative 3 becomes positive 3, and I can distribute the negative 2 through. And now since I want this in slope-intercept form, I have to solve for y by subtracting 3 on both sides. So I get y equals negative 2x plus 1. So that's the equation of the tangent line. D, sketch the graph of the function and the tangent line. So on your calculator, the function f of x looks like the blue line, and your tangent line is the pink line there, y, and they are tangent at the point 2 comma negative 3. So they share that same point. Existence of a derivative. A derivative does not exist at a point where 1. The function is undefined, so there's a hole or a vertical asymptote. 2. There is a discontinuity, so a hole or a jump in the graph. 3. The limit does not exist, so there's a jump in the graph or a vertical asymptote. 4. There's a vertical tangent line, so the slope is undefined. Or 5. There is a cusp or a sharp turn. So example 5. Find all points where the function does not have a derivative. The graph of the function f of x is given below. Okay, so I'm going to look at this graph from left to right. So the derivative does not exist at x equals negative 2, and that's because you have a sharp turn there. It also does not exist at x equals positive 1, and that's because you have a jump there. And it doesn't exist at x equals 3 because you have a cusp there, or you can think of it as a sharp turn. The derivative doesn't exist at x equals 4 because there's a hole there. It doesn't exist at x equals 5 because you have an asymptote, a vertical asymptote there. And it does not exist at x equals 6 because you have an undefined slope there. So there's a vertical tangent line there. Alright, that's it for this section. Make sure you do the homework.